I would like to talk about search techniques. The first one is depth first search and the second one breadth first search. An example where you can use those techniques would be a simple maze. Let's say you want to find out whether there's a path from the start node, in this case here in the lower right corner, to the goal node in the upper corner. So in this maze you can obviously see a solution. For example, you'd go along those red arrows and you would get from the start to the goal. Or another path would be going first up and then finally to the goal node. So the kind of search problems one can solve with depth first search and breadth first search have the following format. You would be given a set of nodes. Now in the examples before, the nodes would be the cells in the maze. For each node, you would be able to extract the neighbors of a node, so the nodes that you could visit from a node. So again, in the maze, for a cell, the neighbors would be the cell above and below it, and to the right and to the left. And then you also would be given, of course, a source node and a destination node. The source node is a term that's used typically for a start node. And the task would be then to determine if there is a path from the source to the destination node. So let's look at the example maze again. We could label the cells starting with the upper left cell as 0, 0, and then 0, 1, 0, 2, 0, 3, and so on. The source node, remember, was in the lower right corner, so the source node would be cell 4, 4, and the destination node would be cell 0, 0. So we also would have to specify the neighbors of a node. So for example, for node 0, 0, which is up here in this corner, it has only one neighbor, that is cell 1, 0. Or cell 1, 0 up here has the neighbors 0, 2 and 1, 1, and so on. So you have to specify this for each node. Okay, so what are the options to solve a search problem? We look at three brute force search algorithms. The first one would be enumeration, and then we look at depth first search and breadth first search. So enumeration is the least intelligent solution, really, because what you could do is you could just compute all possible node sequences that start with the source node and end in the destination node. And you would just calculate any sequence irregardless if there's a path or not. You just systematically go through those sequences. And then for each sequence, you would check whether it's actually a valid path in the maze. And if you find a valid path, then you know there is a path from the source to the destination. So let's say we have again that maze. So we would start maybe with some node sequence, maybe 4, 4, 3, 3, 2, 2, 1, 1, 0, 0. And then we would check in the maze if that's really valid path. So we start with 4, 4, but then we see already 3, 3 is not a neighboring node of 4, 4, so there would not be a valid path. And we want to calculate the different node sequence. So let's say now we come up with a node sequence 4, 4, 4, 3, 3, 3, 3, 2, 0, 0, for example. So we check again 4, 4, and then we can get indeed to the cell 4, 3, but then 3, 3 is not a neighbor of 4, 3, so that's also not a valid path. So we just keep going on, calculating sequence after sequence, until finally we would get a valid path. So let's say, for example, the path 4, 4, 4, 3, 4, 2, 3, 2, 2, 2, 2, 1, 2, 0, 1, 0, and then finally 0, 0. And then the algorithm would terminate and say, yeah, there is a path from the source to the destination. And it directly also would provide the actual path that leads from the source to the destination node. Now, as you can imagine, there are a lot of node sequences that would have to be calculated unless the algorithm gets lucky and really happens to calculate the actual path at the very beginning. Now it could also, of course, happen there is no path, and then it would go through all the possible node sequences and determine that there is no path. And again, there are so many sequences that this is in general not a practical approach. Okay, here's a smarter approach, and that's depth first search, or often just called DFS. So the idea is you start at the source node and you always just keep going to valid neighbors of the current node. So you really go along a path until you either find the destination, and then of course we're done, or you find somewhere a dead end in the maze, or maybe a cell you have already visited. So in that case, when you reach a dead end or a cell you have already visited, then you would backtrack. So that means you would go to the most recently traversed node and check if there's another direction you can go to. And you keep backtracking until you find such a node, and then go from there and continue on another path. So eventually you also explore, actually in worst case, all these possible paths, and if there is a solution path, it would be found. Now the process where you go back to the most recently traversed node to find another path, that's called backtracking. So you might also find the term backtracking search for depth first search. So let's look again at that example with the maze. So we start here at the start node, and then we just keep going along cells and so on, until in this case we found a dead end. Okay, so now what we do is we go back to the most recently visited cell. But from the cell there's no other way to go, so we backtrack further. And here, see, we have another option to go to the left. So we would keep going to the left, and again we hit a dead end. So we would backtrack again. And now we've explored all the neighbors of this node, so we keep backtracking. Now we have an option to go up. So we keep going again until we hit a dead end, or in this case, we actually find the goal. And now you can see we can use these red arrows in a reverse direction to find the actual path from the start to the goal node. The third option that would be breadth first search, or often called BFS. So in this approach, you would check all the neighbors from the start node. And then from all those neighbors, you look at their neighbors and check if they are a destination. And then you look at the neighbors of the neighbors, and so on, until you find the destination node, or again you've explored all the nodes and determined there is no path from the source to the destination. So let's say we have this maze again. So we would look at the two neighbors of the start node. So let's mark those. So now we have to look at the neighbors of those two marked nodes. So we go one by one, look at all their neighbors. So now we have checked out the neighbors of these two nodes, but now we have found new cells and have to look at their neighbors. So again, one by one, we find their neighbors, and we have now found the neighbors of those previously marked nodes. Now we have to look at the neighbors of the new cells. And so that goes on. So we look at all the neighbors, have found them, and now I have to find the neighbors of the newly marked nodes. We look at their neighbors, and again have found their neighbors, and now look for the neighbors of those nodes. And we look at the neighbors, and now like for this node we have a neighbor to the left and to the right, so that we see the one on the left, but the right has already been found by this node up here, so we don't have to look at this one again. So it keeps going so on. Now this node here is at a dead end, so obviously we can't find a neighbor of this one. Alright, you have to look at those neighbors of the neighbors, and keep moving on. Have found their neighbors, and now that's the only node we have just found in this iteration. So we find its neighbor, which happens to be the goal node, and so now we are done. Now look again at the arrows. If we traverse from the goal node in the reverse direction along those arrows, this leads us again to the start node. And note that no matter which cell you look at, for example here this one on the right, each cell has at most one incoming arrow. So there's a unique path from each cell that actually has an incoming arrow to the start node. It's very interesting to see that breadth first search actually can provide us a path from any node to the start node, or from the start node to any other node that can be reached by the start node through a path. Okay, now the really nice thing here is that both algorithms, depth first search and breadth first search, can be described by almost the same algorithm. They call this a generic search algorithm. The input of the algorithm is an instance of a search problem. So we are given a source node and a destination node, and for each node we can get the neighbors of that node. Again, we want to find out if a solution, that is a path from the source node S to the destination node, exists. All right. What the algorithm also needs is a collection of nodes whose neighbors we still have to explore. So that collection is called next nodes. Now, if you also want to find the actual path at the end that led from the source to the destination, then you can keep track of a predecessor of each node. So that would be like, if you think back of the maze example, that would be for a node, the node from which the arrow comes in. So let's see what the algorithm does. So it starts adding the source node to the list of next nodes to be explored. In order to avoid visiting a node again and again, we mark each node, once we have put it into next node, as selected. So S is marked as selected. Okay? So S will never have an incoming arrow since it's a source node, so we set its predecessor to null. And so far, the predecessor of all the other nodes are also not yet determined. Okay. So while there is still a node in our list of nodes to be explored, we remove a node from next nodes, and we check if that's a destination. Of course, if X is a destination, we are done, and we could use the predecessor information to determine a solution path from the source to the destination. But if X is not a destination node, we have to move on. That means we look at all the neighbors of X, so all the neighbors Y, that have not been marked as selected yet. So we add the neighbor Y to next nodes. And remember now we could add next nodes to the nodes that we have reached because we came from node X. So we set the predecessor of Y to X. Then we mark Y as selected. And take the next neighbor of X, and so on. So now again, in next iteration, you would remove a node from next node, and so on. And so two things can happen here. I mean, either we find at some point the destination node and have found a solution, or eventually next nodes doesn't contain any more nodes. And then the algorithm terminates as well. Now in that case, that means there is actually no path from the source to the destination. And then we would print it and stop. Okay. Now, the behavior of the algorithm depends a lot on how this collection next node is implemented. So here's a real interesting thing. If you want to implement depth first search, you could use a stack to implement the collection next nodes, and it gives you exactly the behavior of depth first search. But if you use a queue to implement the collection next nodes, then the generic search algorithm would have the behavior of breadth first search. So feel free to take the maze example and apply the generic search once using a stack and once using a queue, and you will see the different behavior that results.